Hi, my name is Akash Bhatt, and welcome to my presentation on Lab 3 regarding the magnetic field of a bar magnet. In this lab, we were tasked with visualizing the magnetic field of a bar magnet to find the magnitude of the field at separate points in space. We did this by first experimenting with the bar magnet and the magnetometer in our phones, and using our results to calculate the magnetic moment with the Biot-Savart's law. We then created a theoretical model of the magnetic field using our results from the experimental portion of the lab in GlowScript. We used 4 fundamental physics concepts in completing this lab. The first concept we used is Biot-Savart's law, which relates magnetic fields to their sources. We also explored the behavior of magnetic dipoles and how they act similarly to electric dipoles. Another principle we used is how the magnitude of the magnetic field is larger on axis than it is off axis. Finally, we used the concept of the right-hand rule for magnetic fields to determine the direction of the field at a given point in space based off of the current. To complete this experiment, first we determined the position for our bar magnet to compensate for magnetic north by rotating our phone until the Earth's magnetic field had a 0x component. Then we found where exactly in our phone the magnetometer was, and using this position, we measured the distance from the magnet at which the magnetometer produced 5 different magnetic field magnitudes. I made 2 main observations during this experimental portion of the lab. The first observation is that the magnetic field's x component increased as the magnetometer was moved closer and closer to the magnet. The second observation was that the magnetometer measures close to 0 when it is placed far away from the magnet. Here is the Excel table that I filled out when completing the experimental portion of the lab. On the left side is all of the distances that I measured for 3 trials for each magnetic field magnitude. On the right of those numbers is the average, and to the right of all of that is the graph that plots the equation for which matches my data. So as you can see, my equation was y equals negative 3.2432x minus 15.031. We know that the distance dependence is the coefficient of the x here, and that is negative 3.2432. ln of k is the constant here, and that is discovered to be negative 15.031 in my case. Here are my calculations for finding the magnetic moment. I set the ln of k value that we found from the graph equal to the equation of ln of mu naught over 4 pi times 2 mu. Using this, I was able to solve for mu, which I found to be this, 1.24352. We were then tasked to replicate the field of the bar magnet in GlowScript. We needed to visualize the magnitude and direction of the magnetic field at 7 different locations in space, 2 on axis, 4 on a perpendicular axis, and 1 at a 45-degree angle away. To do this, I first needed to create a function that calculated the magnetic field due to the dipole. My code for that portion is shown here, where I calculate the magnitude of the r vector, normalize it, and then use the Biot-Savart equation to calculate the magnitude of the magnetic field. I then created the arrows to show the magnitude and direction at these locations using the function that I created. Here are images of the model created by my GlowScript code. The top image shows the model level with the x-axis. The image below shows the same model at a slight angle to clearly show all of the arrows. I've also included what was printed onto my console. In this image, the orange arrows represent the on-axis magnetic field, and the blue arrows represent the perpendicular axis arrows. The purple arrow represents the arrow at a 45-degree angle. If we had not compensated for magnetic north, we would have not had a 0 value for the x component of the magnetic field. Therefore, our graph would still have a similar shape, but the magnitude of the field we measure will be significantly larger than what we measured when we had compensated for magnetic north. If we lined up 2 magnets, we would have a larger dipole moment. Therefore, this would create a magnetic field that is twice as strong as the one created by the single magnet. This is because the dipole moment is larger with these 2 magnets, and therefore the field will be much greater. This has been my presentation on Lab 3 regarding the magnetic field of a bar magnet. Thank you for watching.